Hi, um, I hope you're having fun with Pulsar Summit and um, you are learning a lot of new things. With this session, we will look at how Pulsar stores your data. So we will sort of look at all the different places in which you have your data, and we will see how this data is stored internally, how this is distributed, how these properties entail what your application should expect out of Pulsar data stores. So first of all, I am SME for Pulsar at Nutanix, and I love distributed systems. I read a lot about it. I try to sort of work as much as I can on distributed system, and I am a huge open source lover as well. Been working on Pulsar lately and done some contributions there. And previously, I've also worked on the MySQL code base, and I have some contributions there as well. Um, so we will look at the modular design of Pulsar, and then we will zoom in on the data store module. We will look at how the data is distributed on the storage internals, and then we will try to sort of also tie all of these pieces together to see how all of them work together to realize the data platform for Pulsar. So first of all, we have 3 layers in Pulsar. The first being serving layer, which actually is where your clients, which are your producers and consumers, connect. And this layer sort of serves all your read and write and all the messaging semantics and all of that. The serving layer actually writes to a storage layer, which stores all the data. And then there is a metadata layer, the same layer that is used by serving layer for its cluster metadata, and storage layer as well uses the same metadata layer. And we will go ahead to look at how they use metadata layer and what are the different things that they store there going ahead. But for now, the serving layer is what we call broker. The storage layer is Bookkeeper, which is an Apache project in its own right. And the metadata layer that Pulsar uses is Zookeeper for both broker and Bookkeeper clusters. So if we look at the data store of Pulsar, this is something that I've highlighted. And on the data store layer, we have Bookkeeper as well as an object store. Bookkeeper is typically where all your data resides. Object store is where some of your old data can move. So your Bookkeeper disks don't grow very, very big when you have a lot of data and you want to retain them for long. So Bookkeeper is your sort of hot or warm storage, and object store is your cold storage. And in addition to that, broker also caches data for multiple topics that this broker owns. And we will go into those ownership semantics going ahead again. So like I said, broker caches some data. Your primary store is Bookkeeper. You can also offload your old data to an object store, which can be different things. And the metadata layer is Zookeeper. For cold store, the JClouds library is what Pulsar uses. And via that library, it has support for storing your cold data on either AWS S3, or you can put it on Google Cloud Storage, or you can use distributed file system like Hadoop or something. So another interesting thing to note here is that although your data initially stays on Bookkeeper, when you offload your data from Pulsar to object store, it's not directly shipped from the Bookkeeper to your object store, and rather it sort of streams from Bookkeeper to your broker to your object store. And this is sort of an interesting choice of implementation. So, I mean, this does take some extra bandwidth, and if it went from directly Bookkeeper to object store, we would obviously save some network bandwidth, but there were some technical constraints with the design of Bookkeeper, which needed to be changed fundamentally. That is why this was the design chosen for that. But what this means is the other syncs like Flink and Presto can't just attach to Bookkeeper to sort of read the data that has been stored by Pulsar. So it has to actually come through Bookkeeper. That is how it would get access to Bookkeeper as well as object store in homogeneous fashion. So like we talked about the model architecture of Pulsar. So because the serving layer, which is broker, and the storage layer, which is Bookkeeper, these are completely different clusters. They can also scale independently. So by scaling your brokers, you're actually scaling your compute. And by scaling your Bookkeeper nodes, you are actually scaling your storage. So there's really a good decoupling where your compute and storage are separate and they can scale independent of each other. So going ahead, Bookkeeper, like I said, is sort of the primary thing here as far as the data storage is concerned. And naturally, we will sort of spend a lot of our time in this session on talking about Bookkeeper. And before we sort of dive in and look at some illustrations on how your data flows within Bookkeeper and gets stored, we will look at some terms that will help us formulate a language that you can use going ahead. So the first bit that we will talk about is journal. Journal is something that is analogous to transaction logs or write ahead log in RDBMS systems like MySQL and Postgres. So when Bookkeeper writes, it first of all writes to journal, which is a non-volatile storage. You have a disk attached to your journal. Journals are generally a little bit smaller in size, and your total journal size doesn't have to be very big. The number of journals is also a little bit limited because, as you'll see going ahead, you can sort of flush your journal files while you are making the new ones. And we create a journal when there's a new bookie or when the threshold that you have defined for the journal size has reached. The second thing that we want to talk about is the ledger. Ledger is actually the basic unit of storage in Bookkeeper. So you write to journal, but you basically read from ledger. We will talk more about those semantics. So if you don't understand these yet, don't worry about those. We will clear that out. Ledger is nothing but a sequence of something called entries. And you can only append to ledgers. You can't go overwrite your older things. And once sort of you have written a certain number of entries and you seal a ledger, you can't really go and change any of it. And that sort of helps when you offload things, because you're not going to write anything there. You just have to take a ledger and move it from Bookkeeper to your object store. Then we talked about entry. So ledger is composed of entries. Entry is where your data is actually sitting as bytes. An entry contains that data plus some metadata, and an entry in Bookkeeper is actually something that maps to a batch of a message in the Pulsar world. Entry log file is actually your physical file where entries reside. These entries could be coming from different Bookkeeper clients. So your brokers in this ecosystem now are your Bookkeeper clients. So different broker nodes could be writing, and these entry files will contain entries from different broker nodes. And these different broker nodes are writing for different topics. So topics sort of write inside ledgers. So you have data from different ledgers, which are sort of together aggregated and written sequentially inside an entry log file. And we have caches on top of these entries for faster lookups. Again, when we have a new bookie, we write a new entry log file. When the threshold reaches, we roll over and make a new ledger file. When you delete stuff, you don't really have free space immediately. It waits for a garbage collector thread to run in the background and check if there is any active ledger that is still sort of using this. If not, then it'll get rid of this file. And for indexing that we talked about, Bookkeeper actually uses RocksDB, which is an implementation of log search merge trees, LSM. And the index actually works in a fashion that the key is ledger ID and entry ID, and the value is the entry log file that we talked about and the exact offset in that physical file where one can find an entry there. So when you sort of go back to look at a message by offset, this is how that could flow through the index to find that exact location in the physical entry log file and the offset there to read that message. So we talked about a topic. A topic is something that is composed of a managed ledger. Ledger, like we talked, are a sequence of entries. A managed ledger also has cursors. Cursors are basically offsets within a subscription. So a subscription S could be reading at a particular location in these ledgers. If we look at what sort of this topic contains in the metadata store, which is Zookeeper, a topic will have ledgers. Every ledger will have a ledger ID, which identifies the ledger uniquely. The entries that are there in the ledger. So then size of this ledger, if this is offloaded to object store or not. And then there are ledgers where the schema of this topic is written, if there are any compacted ledgers and all such things. So if you look at a ledger, so this is the ledger metadata. When you open a ledger, you mark it in a state which is open. Entry ID is -1. Ensemble size is basically your list of bookkeeper nodes on which this ledger is written. Write quorum is basically sort of something like replication factor. How many copies of this ledger do you want to have? How many acts to receive before you confirm a write to the client? And ensembles are sort of at different points of time. Ledger could be written to different bookkeeper nodes, and maybe if one of them goes down, then there's another one that comes and becomes part of the ensemble. So you can have multiple ensemble group for given ledger. So if you write an entry to a ledger, you see that the last entry ID increments, then we write a couple more. And then let's say we say that this is all we wanted to write. So we say that last entry ID was 2 and the status of the ledger is closed. An entry itself has its own metadata. So the ledger ID to which it belongs, the ID of this entry, last I had confirmed is that entry, which is there for the readers to read. And beyond that, we are sort of still in the process of confirming these entries as written to the clients. And then there is checksum, and then you have your actual data that you wanted to write to the entry. If you look at the write paths in Pulsar, right? So you have a client, it sends some data to a topic, let's say X. So it reaches the Pulsar broker, which is the bookkeeper client, writes it to these 3 different bookie nodes. And we are assuming that this is the ensemble on which this ledger that relates to this topic currently is being written. So the client writes to all the three of them parallelly, and it waits for acknowledgements. Let's say if the ACK quorum is 3, then it waits for ACK from all three of them. And then we also sort of register metadata in Zookeeper saying for this topic, if this is a new ledger, then we are also associating that ledger ID with the topic ID inside Zookeeper. So we talked about this. If we look at the read path now, if you read from a topic, the data could be cached on the broker, which is technically metadata ledger cache. You can get data there and you are done. If the data is not there, there's a cache miss, then you go try to read from a broker node, and it could be any of these that you start reading from. And if there is a network partition on this link, then you can just move over to another broker and read from there. We will now look at how data is actually distributed. So if you have multiple topics or multiple namespaces and all, how does data, which is sort of one space as a group, get distributed in the broker, bookkeeper sort of together? And that will give us a nice layout of how things happen internally and what properties among consistency, availability, latency, and throughput can we expect, right? So Pulsar is a multi-tenant system. So you have a tenant, and within a tenant, you have namespaces. Each namespace actually has a lot of topics, which are grouped as something called bundles. Bundles are basically the units on which load balancer works. So if one topic, one bundle is very overloaded, then it can sort of reorganize itself, and maybe a bundle can move from one broker to another broker. So you see bundle is actually a list of some of the topics that belong to a namespace, and the other remaining topics will be part of another bundles. If you look at a topic we have already discussed this, is actually composed of ledgers and cursors, which are basically offsets in these ledger files for different subscriptions. And then you look at entries as part of these ledgers. And you can see that this orange is sort of 2 different entries, and that is replicated onto different sort of ledgers. The blue one is actually replicated twice. The replication factor was 2, and the yellow one is here, and maybe there's another ledger file on which this is replicated. Bookkeeper is a system that sort of, in the event of a network partition, chooses consistency. So it's a CP system going by the conventional CAP definition. So your distribution is something that you can configure. And for that, you have 3 hooks, which is ensemble, write quorum, and act quorum. Ensemble is the list of bookies that this ledger is being written to. Write throughput is your, so I mean, if you have a bigger ensemble, bigger list of bookies on which you're writing the ledger, obviously you have a lot of IO and different places to write to. So your write throughput actually increases. Write quorum is your replication factor. So if you keep it higher, then you have a good HA system. ACK quorum is the number of bookie nodes which have confirmed to have written this, and the acknowledgement has reached the ACK collector. So if you have a big ACK quorum number, so you have a lower latency actually, but you still want to have sort of some good number of ACK quorum, because then you are always sure that at least that many copies are written before you ACK to the client. So, I mean, you can, depending on the use case, do a good trade-off on how much throughput, how much HA, and how much latency do you need with these configuration options. So going ahead, then in the Bookkeeper, we have these two very important concepts, which is last act confirmed and last act pushed. So you look at a ledger, and then there are a lot of entries that are written to this ledger. Last act confirmed is actually the last entry in this ledger um, for which we have committed to the client as something that has been written. So the readers can read until this point. For the blue ones, you see that these have been pushed for the broker nodes to be written on this ledger, but we have not had enough writes done, or we have not gotten enough acts. So we are waiting for those, for these to be visible to the readers, because Bookkeeper guarantees that if one reader can read something, it has to be there for other readers. And at the same time, if something is confirmed as written to the client, it should always be available for the readers. So these blue ones are sort of still in that process where they're not committed to the client as having been written. And last add pushed is where sort of your write on this ledger, on this bookie node, is actually writing right now. So your LAC to lap is sort of the entries that are being written currently and not confirmed yet. The last add confirmed pointer is not something that is persisted and having to sort of go and look at it all the time. When you write a ledger, in the response you get back last add confirmed. So the writer application actually knows what is the last entry till which it can read. And if a writer, by the way, crashes while it is writing, then there is a new writer, it comes up, it sort of starts writing in a new ledger file. And what happens is this new writer first goes ahead and fences this. Fencing is again something that happens by consensus, where enough book is confirmed that we can close this ledger. Then the new writer actually goes and closes this ledger and start writing. And what it gives us is, if there was a split brain, this was the split brain situation, then the old writer cannot come back and write to the same ledger again. So we don't really have that split brain problem here. We talked about fencing, so like we could have a recovery, and the new bookie sort of that starts to own that, will actually fence the ledger and then start with the new one. We'll now look at sort of some more Bookkeeper internals with some pictures. But first, we need to sort of know that Bookkeeper doesn't have sort of different responsibilities for different nodes. So each node is only concentrating on writing to the disk as efficiently as it can. The replication, consistency, coordination, and all of that is actually something that the Bookkeeper client handles. And the Bookkeeper nodes actually have very simple APIs. So you can write sort of entry to a ledger. You can create a ledger in a synchronous fashion or in synchronous fashion. You can read an entry from a ledger. You can delete a ledger. You can't delete an entry in a ledger. You have to sort of delete the ledger. So like we look at Bookkeeper client, which is inside our broker. Then we have a lot of journal files. These are transaction logs inside the Bookkeeper server. And if we look at an active journal, so there are journals which are written, they are full and they are closed, we rolled over and got a new active journal, and we want to write some entries into Bookkeeper. So we go write entries for a ledger in the Bookkeeper. So ledger 1 entry 0, ledger 1 entry 1, ledger 1 entry 2, these are written. Then we get entries for different ledgers. So we have two entries from L2, then we have one entry from L1 again, and one entry from L2, and another entry from L3. I basically color coded ledgers in a way that one color represents one ledger. So the right to journal is actually the first step in a right to the bookkeeper. We talked about what journal is. So it not only writes to journal, but it also in the synchronous path, when you write to bookkeeper storage node, writes to write cache, which is an in-memory structure. So you can read from memory asynchronously, though thread will come and flush the data that is there in write cache. In write cache, you can see that the entries from the same ledger are sort of kept together. This will help us with faster reads by avoiding random IO when we come reading entries from that same ledger. So when it flushes again, it writes to read cache, and it also sort of writes to the entry log file. And I mean, while there is read cache in memory, everything that is written to entry log file is also written to an index store. So we talked about this. Every entry in Bookkeeper is actually a batch of a message in Pulsar, and this flush happens asynchronously. So if you go back, you look at this API, so it writes to journal, write cache, and then just returns, and then this flush happens asynchronously. And with every entry that is written to an entry log file, there is an index that the bookkeeper maintains. Pulsar uses the RocksDB index. So you basically have a ledger ID and an entry ID, and that basically maps to an entry log file and a specific offset in that entry log file. So you can just follow this pointer and go to the exact entry in an entry log file on the physical file system. And that's how we map this logical concept of a ledger to a specific offset on a physical file to read that message in Pulsar or an entry in the Bookkeeper. So if we summarize this, you see this light green color. When we write to a journal file, then we write to a write cache. Asynchronously, you see with this dark green, we write to entry log file, and we also write to index file, which is RocksDB in implementation. So you see that journal has its own dedicated disk, and your entry log file, which is basically your ledgers, has its own disk. So we have got writes going here and reads going here. So we really have a good level of IO isolation. So if you're reading some old data or backlog data, right, that's not there in the caches, that's not going to affect your publisher writing, because this is in a completely different disk. It could overboard this, but not this. And this is some sort of really interesting things. Like I said earlier, we don't have schema information in the Bookkeeper storage. It's a very, very simple byte storage system. Bookkeeper client actually writes its metadata to Zookeeper, and sort of the bytes in the entries to Bookkeeper storage nodes, which are bookies. In addition to metadata about entries, it also uses Zookeeper for service discovery and garbage collection. So if you look at the metadata for a specific ledger, it has format version, it has ensemble size, which is how many bookies it is being written to, write quorum, which is replication factor. We talked about this, act quorum, how many acts are required. The state of this ledger that we're talking about is closed. It could be open, it could be in recovery or anything. The length of this ledger, the last entry, which is part of this ledger, checksum, the different ensembles at different point of time, and as part of the first ensemble, what's the range of entries of this ledger. as part of the second ensemble, what are the a range of entry IDs you can find in these bookkeeper ensembles. And then there is some custom metadata where Pulsar stores sort of the topic to which this ledger is bound here. So we talked about this earlier as well. Entry log file is what actually exists on the physical disk. Ledger is a logical concept, sort of it's a linked list kind of a structure where you have entries that span in physical different bookkeeper nodes, and sort of even within the bookkeeper node, different entry log files, and it sort of still constitutes one ledger with these links from metadata store to a map into the exact physical offsets on which these entries are written on entry log file. So the another interesting observation is that so consistency logic, which is maintained in the client, is completely decoupled from the physical storage. All the application and all those things that happen with the ledger file. Physical storage is actually very, very dumb. So when you write to bookkeeper, the synchronous path only writes to journal, and there's an in-memory write cache. We talked about it. We have separate disks for journal and ledger, so the IO contention doesn't happen. And that means that we talked about this again, where sort of backlog where you want to read older data doesn't really affect your write throughput at this moment. So on the metadata layer, again, summarizing everything, what do we store? We store sort of 5 different kinds of things that I have listed here. In this slide, you can see 3 of them. So pointers to data. With a topic, we have mappings of which ledgers that store the data relating to this topic. With ledgers, we know, we saw earlier that ledgers in custom metadata tell you which topic it belongs to, which topic is mapped to which schema. That is there in metadata layer again on the Zookeeper. Service discovery is something that happens through metadata layer in Zookeeper again. So Zookeeper will tell you the list of available book keys, which book keys are there to be read and written, the list of available brokers as well, which broker owns which topic. I think we didn't touch off ownership concept as much, but the whole point is that at one point of time, a topic has only one owner broker. Only that broker will serve the read and write on that topic, which allows Pulsar to cache data for that topic on this broker. And this broker then can also sort of single-handedly manage the replication factor and all those things directly right to broker nodes. For load balancing, we also want to know which topic has how much load. So the topic be kept on a broker, or if this broker has too much load, then depending on that, different algorithms, we could select a topic and move it over from one broker to another broker, so the load is sort of evenly balanced among the broker nodes. We also use sort of the metadata layer for locks, distributor locks, leader election, and bookkeeper nodes. Then we also have system configuration. So you don't want to restart your broker nodes or bookkeeper nodes for every configuration change to take effect. So you use Zookeeper watches to push these changes to brokers. And then there are feature flags that you can keep again on Zookeeper watch. Then there is provisioning configuration like metadata for tenants, the exact configuration for a namespace, which is technically namespace policies, tenant to namespace mapping, namespace to topic mapping, and all those things that are kept in the Zookeeper layer. So that's it. most of my knowledge about Bookkeeper has been based on some amazing sources that are out there. So I'll share those with you so you can go read about more of them. The first is amazing blog by Jack on how Pulsar actually works. Then you have others, some from the Stream Native team, and some from Verizon Media and Splunk and all. And I'll leave this presentation on SlideShare, and I'll put a link on the Slack channel and my own LinkedIn and all. If you have a question, you can drop it on Slack, or you can sort of just send me a hello if you want. If you have any questions, then you can ask me even now if you have time.